Yeah, so today I wanted to talk about trees, different types of trees. So that is the one moment. Yeah, so that is the cornerstone in computer science, the the trees theory. So yeah, and because they are
Slow
used
down,
everywhere.
slow down, slow down,
Yeah, all
slow
right.
down. Okay,
Yeah, and
okay.
because these trees are used everywhere in as both in computer science and in real world situations. Yeah, so they're very useful. They're yeah, the
Okay.
very fabric of how we organize data, make decisions, and software. Yeah, so there are various applications of these trees and computer science. So yeah, today we're going to cover the definition, the mathematical identification of these trees versus a standard graph. Then we'll look at its real-world applications of where they appear from HTML to graph theory or to game theory. And then we'll talk about how to store and represent graphs and compare. We're going to we're going to compare different types of trees. Yeah, there are some specialized trees we're going to talk today. Yeah, and a bit of details about implementation of the grease, how we can implement them on code. Yeah, so let's start with the basics. What actually defines a tree? So between these four graphs, there is only one of them which is a tree, which is not a one moment, which is not a tree. So only one of these is not a tree. So which one of them does not?
The one on the end, the one on the end.
Yeah. This thing, yeah. The last graph is not a tree, because the
Because I
definition.
listened to
We
Vadim. I listened to Vadim, and then he told me before this was not a tree. So
Yeah
go ahead.
yeah yeah that's it, yeah. Yeah, because we define a tree as being an undirected graph, not always undirected, by the way, with no cycles, and that the key thing to remember here is that these trees cannot have cycles. Yeah, and also it might be, and this graph has to be connected. Yeah, so here the rightmost graph has a cycle, so that is not a tree. However, there is an easier way to check whether the graph is tree or not, which we used in series. That is, uh, we want to take into consideration if the tree, if a graph has exactly n nodes and n minus 1 edges. So we count up all the nodes and edges, and we want, yeah, and also in this case, if uh, there are one less nodes than there are one less edges than nodes, if there are n nodes and n minus 1 edges. This we really want to check if the graph is connected, because if it is not connected, that means it is not a tree. Yeah, and so here each graph is connected. The first three are connected graphs, and they have 4 and 4 minus 1, 3 edges, and so on, 6 and 5, 13 and 12. But the last one has 7 nodes and 8 edges, so therefore that is not a tree. All right, yeah. So let's now look at how do these trees appear in computer science and in real world situations. So here are a few examples where we might encounter these trees. Yeah, so the first, oh, right. Yeah, so the first the first example when we can encounter these trees is file system in a computer. So it consists of directories, these subdirectories, and files. So that is a tree. There might not be any of the cycles, and the file system might not be disconnected, yeah, unconnected, and that is why that is a tree. So also social these how this word
What hierarchies?
yeah,
Hierarchies.
hierarchies. All right. Yeah,
Okay.
so that is also when we can encounter a tree with the CEOs or kings or presidents, whatever, at the top, and interns or children, whatever, at the lower class at the bottom. So another example is abstract syntax trees. That is the mathematical usage of these, the mathematical yeah, the
Mathematical
case,
representation.
yeah, mathematical representation. The case we're using them here is these abstract syntax trees. So in this way, we're decomposing source code and mathematical expressions for easy evaluation into a tree in this way. And also, every web page we visit on the internet can be thought of as a tree. So we can think of each of the web page we visit as a tree. Yeah, because these HTML DOM structure, so that is HTML's nested tag structure, it used to tell the browser how to easily render the page and how it should be displayed. And yeah, this is why we use trees to represent the structure of a web page, and also another one moment.
Confess.
Yeah, yeah, another
Oh,
large application of trees is that is the game theory. This is the example with Prisoner's Dilemma. So this is, yeah, the very famous problem, and here is the how we can represent it. There are 4 outcomes. So each prisoner has 2 options to confess or to defect. So if we are making 2 rounds of this problem, there might be 4 outcomes, and there might be greater for larger amounts of rounds. And next, is many other applications, many more applications of trees and computer science and real world. That is, for example, memory trees, or and also computer science and programming. There are such applications as data structures, that is AVL trees, B trees, red-black trees, and many more, segment, Fenwick, whatever. That is the countless amount of these representations in real world of these trees. And this is why we consider them as pretty useful. Yeah, and now let's move on to talking about how we actually store these trees and represent them. So let's start with undirected trees. To represent them, we want to start by labeling all the nodes in a tree from 0 to n, non-inclusive. This is how it's represented on the left side. And next, the first way of representation, the most simplest, as we've looked, previously, 3 ways. So the first way here, using these 3 types we already know. These AdjaList, adjacency list and adjacency matrix. So let's consider all of these three ways, and let's look at which is better to use while working with trees and while working on different problems with trees. So yeah, let's look at the advantages of using Adjalist as the representation, as the storage representation of undirected trees. It just indicates the two nodes, and the pair contains which the edges between the two nodes. So a great way and a great thing about this representation is that it is super fast to iterate over each edge. So in some algorithms that might be useful, and also it is very cheap to store. We have just a we have a list of n, an array,
okay,
of n minus 1 pairs, and its space complexity is very cheap.
Okay.
And but the downside, however, is that storing the tree as a list lacks the structure, so we cannot efficiently query all the neighbors of the node. However, we can do this inside an adjacency list. So this is why the adjacency list is usually a more popular solution, more popular decision to store an undirected graph, an undirected tree, to be more accurate. So in this representation, you store a mapping between a node and all its neighbors. Here how it works, just we can make it as a map or dictionary in Python. However, it is much more easier just to store this mapping using a list of lists. Vector of vectors in C++, whatever. So in this way, we can find out all of these. We can easily find out all of the neighbors of a particular node, and this is why this algorithm is much more efficient. So for example, on the 4 node, for node 4 has the neighbors 1, 5, and 8, and we can see that from the that node 4 maps to the list containing 1, 5, and 8 respectively. So also we can represent a tree as an adjacency matrix size n by n. However, that is very inefficient to use this. Let's look at why. In practice, I would say to never use this in this way, to avoid storing a tree as an adjacency matrix, because we use n squared time complexity, n squared memory, and we use only 2n roughly of the matrix cells. So this does not make sense. So there are n squared minus 2n cells empty, and that is nonsense, of course. So this is why we would most commonly use these adjacency lists while working with trees, because in this way we can start some recursion algorithms such as DFS or even BFS a lot more efficiently on these, because we can query all the neighbors of the node, we can traverse all the neighbors of the node, and of course with the edge list or even with the adjacency matrix, that is much more inefficient to do this. And that is what about storing and representing trees. And now let's look at some specialized types of these trees. The first thing we want to talk about is, by the way, I can't keep talking about trees without mentioning these trees, this type of trees, that is rooted trees. So these are the trees which with a designed root node. So, for example, here the root node has highlighted in orange, and the rooted tree, these in the example, and so generally speaking, these rooted trees are far easier to work with than undirected trees because they have a very well-defined structure. They have a root node, all the children of this node, and so on, without all these infinitive amounts of neighbors, which can be cycled even if, because of course a tree does not contain a cycle. However, we can make these while iterating a breadth first, if we won't have a used array or color array, whatever. And this way, with rooted trees, it allows us for easy recursive algorithm implementations. All these algorithms with DFS, BFS, whatever. And the next type of tree is a binary tree. So related to rooted trees, of course, these are binary trees. So in this tree, each node has at most 2 child nodes. So these 2 trees are binary nodes because each node contains no more than 2 child nodes. And the third one is not, because these right node has 3 children. So in the real world, there are not many representations or real world applications of these binary trees. They do not often manifest themselves in the real world. However, they are created artificially and manually, and they're integrated to numerous amount of data structures. So they are making search operations much more efficient. So that is why we want to consider using them here. So also it allows us efficient insertions, removals, and access to data. So for example, SAT, multi-SAT, unordered SAT, and all of these 3, not the unordered SAT, all these SAT and ordered SAT types and map types in C++ are implemented using binary trees, using specialized type of these.
Using what? Using what?
Using these specialized types of trees. So as I know, using AVL or red black tree, I do not sure, but using something like a binary search tree. And now let's look at what is a binary search tree. So as I know, SAT data structure the set data structure uses something like that. Binary search trees, they satisfy the BST, binary search tree invariant. So that is, for every node X, left value, its left child's value is less or equal than the X, and its right value is greater or equal than X. So in this case, there's an invariant. To satisfy this invariant, it must satisfy this double inequality. And this way how it works. So this property enables to quickly search at a tree in the time complexity of in the logarithmic time complexity, the O of log n time complexity, to retrieve the values we want. That is particularly handy. So all the trees on this slide are binary search trees, except for the last one. So here, one node that is right node of 3 does not satisfy the binary search tree invariant, since it is not greater or equal to 3. Yeah, all right. And the next thing is that in some cases it is often useful to require uniqueness of the value. So here we have a strict inequality rather than greater, less or equal. We have just less, and it guarantees that there are no duplicates, or duplicates.
Duplicates.
Yeah.
Yeah.
Yeah, yeah, it guarantees that there are no duplicates in the tree, and this is how a set works. And with this greater or equal, with or equal part, that is the multi-set, how it is implemented in C++. Yeah, so these all the differences are just in one more sign of equality. Yeah, and now let's talk about how to store these rooted trees. So they are naturally defined recursively in a top-down manner. Yeah, so in practice, we always maintain a pointer reference to the root node, so we can access the tree and its contents, and each node has access to the list of its children. So these are known as child nodes. In this slide, the orange node is the current node we have a reference to, and the purple nodes are all its children. We also have, we can access from this node. And all the bottom, our leaf nodes, does not have any children. So sometimes it is also we have to maintain a pointer to the node's parent node in case we need to traverse up the tree. So sometimes it might be helpful. And this effectively makes the edges in the tree bidirectional. That makes them some kind of an ordered, not an ordered, but undirected, but that is not an undirected ref. Yep. In pink, there is a parent node in these slides. So usually it is necessary we can access a node's parent on recursion function callback. To have the ability to make the recursion functions, to make these callbacks on the recursion stack. As we pop these elements from the recursion stack. We must have this access to a node's. We should have this access to a node's parent node. Yeah, but another really neat way of storing a root tree is to represent a binary tree. We can represent this way only a binary tree with an array, or flattened array. Not this array of arrays, not vector of vectors, but just an ordinary, normal array. So in this flattened array representation, each node has an assigned index position. So it is based on where it is in the tree. And the thing to understand here is that the tree is actually an array. Yeah, these diagrams are just a visual representation, and of course, any graph is just a visual representation of their real computer representation. Yeah, but for example, for instance, node 5, the node with value 5 is associated with the index 4 in the array. And the trick, I want to show how to use this. Yeah, so For example, for node 2, it has the index of 6. And so even nodes that are not currently present in the array, we can already map there. Yeah, that is known as index trees. Yeah, and the very important thing for storing rooted trees, yeah, these formulas are are vital for this trees theory, is that these formulas. So in this format, the root node has always index 0, and we can access any node's children. These two formulas. The left children is 2 times current position plus 1, and the right node 2 times current position plus 2. And then this way, with these two formulas, we can access all children node of a node in a of 1 time complexity, and also this increased time complexity very much, by the way. So for a position 2, we know that the left children is 2 times 2 plus 1, that is 5, at the position 5, and the right children is at position 2. Yeah, so this is how it works. This representation of so therefore, the children of the node at index 2 can be found on positions 5 and 6. So that means that we have a node. We know at the index by the parent node, and also we can backwards we can find the parent node in this formula. Yeah. Yeah. So that's it for this video. And to wrap things up, today we've seen what trees are, and we've seen that these trees are far more important than just graphs without cycles, or graphs with n-1 edges. So these are these very versatile data structure, yeah, and which has numerous amount of properties that we can use practically in computer science. So we've explored today how to store these structures effectively with a lot of different representations, about 5 representations of both undirected graphs and undirected trees and rooted trees, and also we've learned how to handle binary trees using these simple formulas, and yeah, so I'll wrap up here. Thank you, Robert.
Sure. Yeah. Hey, just in the future, Vadim, just slow down a little bit, okay? Because see, sometimes when you speak too fast, I hear something, but I'm not confident that I heard you correctly. So it might be correct, it might not be, so I skipped that, okay? But the ones that I did hear, I wrote down, okay? But thank you.
Yeah, all right.
Thank you for your preparation. Yeah, but just slow down a little bit so that I can analyze what you said. So, okay. But thank you.